NEC Article 250.4. A5 requires the equipment grounding conductor to provide a low impedance path for fault current. This path facilitates the operation of an overcurrent protective device, specifically a circuit breaker, when a fault occurs on a circuit. The goal is to ensure that when a short circuit or ground fault happens, the fault current is high enough to quickly trip the breaker, disconnecting the circuit and preventing potential hazards such as fire or electrical shock. To achieve this, the available fault current at an outlet must exceed the threshold current required to trigger the magnetic response of the circuit breaker protecting that outlet. The magnetic response is a fast, instantaneous trip mechanism within the breaker. If the fault current is below this threshold, the breaker will not trip quickly, and the requirements of NEC Article 250.4. A5 will not be met, even if the equipment grounding conductor is fully compliant with all other requirements of Article 250. Recent test data gathered from short-circuit tests conducted at 120 volts receptacle outlets in residences indicates a concerning trend. More than half of all circuit breakers installed to protect 120 volts outlets on 15 amps and 20 amps branch circuits do not provide an instantaneous response to a short circuit at an outlet in the circuit. These tests involved creating a bolted short circuit at receptacle outlets on 15 amps or 20 amps branch circuits using a field test instrument. The results showed that a significant percentage of breakers exhibited a thermal response, which is slower than 1 cycle, rather than the desired magnetic response of 1 cycle or faster. This means that in many cases, breakers are not tripping quickly enough to effectively protect against short circuits. To address this issue, Proposal 10.55 to the 2008 NEC was introduced. This proposal aimed to clarify expectations for the NEC user regarding the response of dwelling unit branch circuit breakers to short circuits or ground faults. The proposal standardized the threshold current for the magnetic trip in circuit breakers at 11 times the handle rating of the breaker and required magnetic response clearing times of 1 cycle. For example, a 15 amps breaker would need to trip instantaneously at 165 amps, which is 11 times 15. A subsequent proposal to Article 210 in the 2011 NEC addressed voltage drop. This proposal requires that the voltage drop at the furthest outlet of a 120 volts branch circuit not exceed 9%. Limiting the voltage drop ensures that the available fault current at the furthest outlet of a branch circuit will be sufficient to trigger the magnetic response of a breaker that meets the requirements of Proposal 10.55. Voltage drop is the reduction in voltage that occurs along the length of a wire due to its impedance. Higher impedance results in greater voltage drop. Excessive voltage drop can reduce the available fault current at the end of the circuit, making it harder for the breaker to trip quickly. If both proposals are accepted, they will establish an impedance-based limitation on the length of a branch circuit of a given size. This limitation will ensure that all outlets are protected from short circuits or ground faults by an effective instantaneous circuit breaker response that will clear in 1 cycle. In essence, these changes aim to create safer electrical systems by ensuring that circuit breakers trip quickly and reliably in the event of a fault. This is achieved by setting clear standards for magnetic trip thresholds and by limiting voltage drop to maintain sufficient fault current throughout the circuit. NEC Article 250.4. A5 is crucial for electrical safety. It mandates that equipment grounding conductors offer a low impedance path for fault current, thereby activating overcurrent protection devices, such as circuit breakers, during a fault. The underlying principle is to ensure that any short circuit or ground fault triggers a rapid response from the breaker, effectively cutting off the power and preventing potential hazards like fires or electrical shocks. The magnetic response threshold of a circuit breaker is a critical factor in this process. For a breaker to trip instantaneously via its magnetic mechanism, the available fault current at the outlet must surpass a specific threshold. This threshold is the minimum current required to activate the magnetic trip, causing the breaker to open the circuit almost immediately. However, recent test data has revealed a concerning trend. Tests conducted on 120 volts receptacle outlets in residential settings indicate that a significant number of circuit breakers, particularly those protecting 15 amps and 20 amps branch circuits, do not provide an instantaneous response to short circuits. This suggests that the available fault current at these outlets is often insufficient to trigger the magnetic trip of the installed breakers. To address this issue, NEC Proposal 10.55 was introduced. This proposal aims to standardize the magnetic trip threshold current at 11 times the breaker's handle rating. It also requires magnetic response clearing times to be within 1 cycle. This standardization is intended to ensure a more consistent and reliable response from circuit breakers during fault conditions. For instance, a 20 amps breaker, according to this proposal, should trip instantaneously when the current reaches 220 amps, which is 11 times 20. This would ensure quick disconnection in the case of a short circuit. Complementing this, a subsequent proposal was made to Article 210 of the NEC, focusing on voltage drop. This proposal limits the voltage drop at the furthest outlet of a 120 volts branch circuit to a maximum of 9%. By limiting voltage drop, the proposal ensures that the available fault current at all outlets remains sufficient to trigger the magnetic response of breakers meeting the criteria outlined in Proposal 10.55. This is because excessive voltage drop can reduce the fault current to levels below the breaker's trip threshold, compromising safety. The combined effect of these proposals is a system where branch circuits are subject to impedance-based length limitations. These limitations are designed to ensure that every outlet in the circuit is adequately protected against short circuits and ground faults, with circuit breakers responding instantaneously and clearing the fault within 1 cycle. The end goal is enhanced electrical safety through a more robust and reliable overcurrent protection system. In summary, the equipment grounding conductor, as mandated by NEC Article 250.4, A5 plays a pivotal role in facilitating the operation of overcurrent protection devices. This ensures that circuit breakers can respond quickly to fault currents, preventing potential hazards. The magnetic response threshold of a circuit breaker is crucial because it determines the speed at which the breaker trips during a fault. Standardizing this threshold, as proposed in NEC Proposal 10.55, along with limiting voltage drop as per the subsequent proposal, aims to create a more reliable and safer electrical system. These measures collectively work to ensure that electrical circuits are protected from short circuits and ground faults by a dependable and instantaneous circuit breaker response. Now let's delve deeper into the technical aspects of NEC Article 250.4, A5 and the related proposals. The purpose of NEC Article 250.4 A5 is to establish a fundamental requirement for electrical safety. It mandates that the equipment grounding conductor provide a low impedance path to facilitate the operation of overcurrent protective devices. This means that when a fault occurs, the grounding conductor must provide a clear and unobstructed path for the fault current to flow back to the source. A low impedance is critical because it ensures that the fault current is high enough to quickly trip the circuit breaker. Without a low impedance path, the fault current may be limited, preventing the breaker from tripping and creating a dangerous situation. The magnetic response of the circuit breaker is one of the 2 primary mechanisms by which it trips. The other is thermal response. The magnetic response is designed to provide instantaneous protection against high fault currents, such as those that occur during a short circuit. When the current exceeds a certain threshold, a magnetic field is created within the breaker that trips the mechanism, opening the circuit. The thermal response, on the other hand, is slower and is designed to protect against sustained overloads. The thermal response relies on a bimetallic strip that heats up and bends when the current exceeds the breaker's rating for an extended period. The bending of the strip trips the breaker. The test data revealing that a significant percentage of breakers do not provide an instantaneous response highlights a potential weakness in the existing electrical systems. This issue may be due to several factors, including the use of breakers with high magnetic trip thresholds, long circuit runs with high impedance, and poor connections that increase resistance. The fact that many breakers exhibit a thermal response instead of a magnetic response suggests that the fault current is not high enough to trigger the instantaneous trip mechanism. This can lead to delayed tripping, which increases the risk of fire and electrical shock. NEC Proposal 10.55 seeks to address this issue by standardizing the magnetic trip threshold and requiring faster clearing times. By setting a clear standard for the magnetic trip threshold, the proposal aims to ensure that all breakers will trip quickly and reliably in the event of a short circuit. The requirement for one-cycle clearing times further enhances safety by minimizing the duration of the fault. The subsequent proposal to Article 210, which limits voltage drop, is also crucial for ensuring effective overcurrent protection. Voltage drop can significantly reduce the available fault current at the end of a circuit, especially in long runs. By limiting voltage drop to 9%, the proposal ensures that the fault current remains high enough to trigger the magnetic response of the breaker. This proposal works in conjunction with Proposal 10.55 to provide a comprehensive approach to overcurrent protection. In addition to these proposals, proper installation and maintenance are essential for ensuring the effectiveness of circuit breakers. This includes using the correct size conductors, making tight connections, and regularly inspecting the electrical system for any signs of damage or deterioration. It is also important to choose circuit breakers that are appropriately rated for the circuit and the load they are protecting. Choosing breakers with lower magnetic trip thresholds can improve the instantaneous response to short circuits. By following these best practices and adhering to the requirements of the NEC, it is possible to create safer and more reliable electrical systems. The combination of a low-impedance grounding path, standardized magnetic trip thresholds, and limited voltage drop provides a robust defense against electrical hazard. In conclusion, the technical aspects of NEC Article 250.4 A5 and the related proposals are critical for understanding how electrical systems are designed to protect against short circuits and ground faults. By ensuring a low-impedance grounding path, standardizing magnetic trip thresholds, and limiting voltage drop, these requirements work together to create a safer electrical environment. Remember, this is a complex area of electrical engineering, and it is always best to consult with a qualified electrician for any electrical work or questions. Let's further examine the practical implications of these NEC requirements and proposals. In real-world scenarios, the implementation of NEC Article 250.4 A5 and the related proposals has a direct impact on the safety and reliability of electrical systems in residential, commercial, and industrial settings. Consider a typical residential wiring scenario. In an older home, the electrical system may have been installed before the current NEC requirements were in place. This means that the grounding conductors may not be properly sized or installed, and the circuit breakers may have high magnetic trip thresholds. In such a case, a short circuit at an outlet could result in a delay breaker trip or even no trip at all. This could lead to overheating of the wiring, potentially causing a fire. By upgrading the electrical system to meet current NEC requirements, including ensuring a low-impedance grounding path and installing circuit breakers with appropriate magnetic trip thresholds, the risk of fire can be significantly reduced. The proposals to standardize magnetic trip thresholds and limit voltage drop also have practical implications for new construction and renovations. For example, when designing a new electrical system for a home, the electrician must carefully consider the length of the branch circuits and the size of the conductors to ensure that voltage drop is within acceptable limits. They must also choose circuit breakers that meet the standardized magnetic trip thresholds. This may require using larger conductors or installing additional branch circuits to minimize voltage drop and ensure that the fault current is sufficient to trip the breakers quickly. In commercial and industrial settings, the implications of these requirements are even more significant. These environments often have complex electrical systems with high loads and long circuit runs. A short circuit in such a system can result in significant damage, downtime, and even injury. By implementing NEC Article 250.4 A5 and the related proposals, businesses can protect their assets and employees from electrical hazards. This may involve conducting regular inspections of the electrical system, upgrading grounding conductors, and installing circuit breakers with appropriate magnetic trip thresholds. It is also important to consider the impact of voltage drop in these environments. Long circuit runs and high loads can result in significant voltage drop, which can affect the performance of equipment and reduce the effectiveness of overcurrent protection. By limiting voltage drop, businesses can ensure that their equipment operates efficiently and that the circuit breakers will trip quickly in the event of a fault. In addition to these practical considerations, it is important to be aware of the legal and regulatory implications of NEC compliance. In many jurisdictions, electrical installations must comply with the NEC, and failure to do so can result in fines, penalties, and even legal action. Insurance companies may also require compliance with the NEC as a condition of coverage. Therefore, it is essential for electricians, contractors, and building owners to understand and adhere to the requirements of the NEC. This requires ongoing education and training to stay up to date with the latest changes and interpretations of the code. In conclusion, the practical implications of NEC Article 250.4 A5 and the related proposals are far-reaching and affect the safety and reliability of electrical systems in all types of buildings and environments. By understanding and implementing these requirements, it is possible to reduce the risk of electrical hazards and protect people and property from harm. Let's now explore the specific calculations and methods used to ensure compliance with these NEC requirements. To comply with NEC Article 250.4 A5 and the related proposals, several calculations and methods must be employed. These calculations help determine the appropriate size of grounding conductors, the expected fault current at various points in the circuit, and the voltage drop along the circuit. The first step in ensuring compliance is to determine the required size of the equipment grounding conductor. NEC Table 250.122 provides guidance on the minimum size of the equipment grounding conductor based on the size of the overcurrent protective device protecting the circuit. For example, if the overcurrent protective device is rated at 20 amps, the minimum size of the equipment grounding conductor is typically 12 American wire gauge copper. However, it is important to note that this is just the minimum size, and in some cases, a larger grounding conductor may be required to ensure a low impedance path. To determine the expected fault current at various points in the circuit, a fault current calculation must be performed. This calculation takes into account the voltage of the circuit, the impedance of the transformer or other power source, and the impedance of the circuit conductors. The formula for calculating fault current is typically I equals volts divided by Z, where I is the fault current in amps, volts is the voltage of the circuit, and Z is the total impedance of the circuit. The impedance of the circuit conductors can be calculated using tables provided in NEC or by using specialized software. The calculation should be performed at the service entrance and at the furthest outlet on each branch circuit to ensure that the available fault current is sufficient to trip the circuit breaker. To limit voltage drop, the NEC recommends that the voltage drop on a branch circuit not exceed 3% and that the total voltage drop from the service entrance to the furthest outlet not exceed 5%. To calculate voltage drop, the following formula can be used. Volts drop equals 2x kxIXD divided by Cm, where volts drop is the voltage drop in volts, K is the constant based on the conductor material. For copper, K equals 12.9, I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils area of the conductor. By calculating the voltage drop at various points in the circuit, the electrician can determine whether the conductors are appropriately sized and whether any adjustments are needed to minimize voltage drop. In addition to these calculations, it is also important to consider the quality of the connections in the electrical system. Loose or corroded connections can significantly increase the impedance of the circuit, reducing the available fault current and increasing voltage drop. Therefore, it is essential to make tight, clean connections using appropriate connectors and tools. Regular inspection and maintenance of the electrical system can also help identify and address any potential problems with connections. Finally, it is important to document all calculations and measurements to demonstrate compliance with the NEC. This documentation should include the size of the grounding conductors, the calculated fault current at various points in the circuit, and the calculated voltage drop along the circuit. This documentation can be helpful in the event of an inspection or a claim. In summary, compliance with NEC Article 250.4. A5 and the related proposals requires a combination of calculations, measurements, and best practices. By following these methods and documenting the results, it is possible to ensure that electrical systems are safe and reliable.